Right, so in the last video we talked about how to make the hypothesis test about the overall significance of the multiple regression, right? We test about all of the betas equals 0 or at least one of the betas not 0, right? So you cannot change the alternative hypothesis by your own words. Some of you say all of them not equals to 0. It doesn't mean at least one of the betas is not 0, right? So it's totally different meaning. So you don't modify this alternative hypothesis, right? And then we use the F-test for the overall significance of the multiple regression. We learned about SST, SSR, SSE. We know how to calculate the F-test statistics, right? And then from the output, right? So, and then based on the p-value, we can get the conclusion about the overall significance of the multiple regression. So next, if after we test about the overall significance of the multiple regression, right? So if the overall significance of the regression is tested and say, okay, the regression is significant right now, right? So that means you rejected the null hypothesis. That means the regression is significant, right? That means I don't know which one explanatory variable have the strong relationship between with the response variable. I just can test overall. There is a relationship, there is linear relationship between the explanatory variables and the response variable. But I don't know which one is the significant or not significant, right? So next, based on the conclusion of the overall significance, we can test for each variable. All right, so next, we will make the hypothesis test for each explanatory variable. All right, so we say we have mu y equals to beta 0 plus beta 1x1 beta 2x2 until beta k xk. Right. Then based on the conclusion here, we say the overall regression is significant. Then I can test for each explanatory variable. I can test about this variable, I can test this variable, and generally we can test about beta j. So this j is equals to 1, 2 until k. That means you can test about beta 1, you can test about beta 2, you can test about all through beta k. So you can test about beta j equals 0 or beta j not equals to 0. Alright, so think about if j equals to 1. That means you will test beta 1 equals 0, beta 1 not equals to 0. Right? So if you want to test about this, what if the null hypothesis is not rejected? That means beta 1 equals 0. This term will be changed to 0. That means there's no significant relationship between x1 and y. Right? So we say if beta 1 equals 0, that means no significant relationship between x1 and the response variable. The same thing, you can test about beta 2, so that if beta 2 equals 0, that means no significant linear relationship between x2 and y. Right, so you can test for any beta, beta 1, beta 2, beta k, but not beta 0. Remember, beta 0 is just an intercept. It doesn't show any relationship between x and y, right? Okay. And since the assumptions are the same, for the second step, you don't need to check the assumptions again, right? And then you can just calculate the test statistics. Since we are not testing all of them, right? We are not testing about all of them. We just test about for each coefficient. That will be just exactly the same when you test about the slope in the simple regression. So you will have t test, which equals to bj divided by standard error of bj. Alright, so that will be based on the sample regression equation, right? So it will be y hat equals to b0 plus b1 x1 plus b2 x2 until bk xk, right? So if you are testing about beta 1, then you will use b1 divided by standard error of b1. If you are testing about beta 2, then you use b2 divided by the standard error of b2, right? Okay, so where to find that? Remember to find in your output, right? In your outputs, you will have the parameter estimates table, right? And then here you will have the b0, b1, b2, and correspondingly you will have standard error of b0, b1, b2. And then you even don't need to calculate the test statistics by the formula if the output is given to you, right? So you have the t-test statistics if you calculate the beta 1, the test statistics for beta 2, and then you have the corresponding p-value, right? You see that for the bedrooms, the p-value is also very, very small, but for the living area, it's even smaller than 0.0001, right? So for both of these cases, the third one, you just find the p-values, right? So for our case, if you are testing about beta 1, then your p-value is equals to, let's check again, is 0.0073, right? And then if you are testing about beta 2, your p-value is very small, it is less than 0.001. So for both of these two cases, it will be you will need to reject the null hypothesis because your p-value is less than any possible alpha, right? So if you reject the null hypothesis, that means these two variables are both significant, right? That means for these two variables, you can make the conclusion for each of them, right? So that means the bedroom, number of bedroom has the significant relationship with the house price. And also for the second test, based on the p-value, that means the living area also has the significant relationship with the price. All right, so this is the first step about the conclusion. Right, so is that easy? Right, so for the hypothesis test for the multiple regression, what you need to do first is to test their overall significance of the regression. Because if overall there's no relationship between the explanatory variable and the response variable, you don't need to check for each one anyway. Right, so first you need to check the overall significance of the regression. If you reject the null hypothesis, then it means the regression is significant. Then you can test for each explanatory variable. You can test about beta 1, beta 2, or beta k for each variable, right? And then you can use the test statistics and p-value to make the conclusion. All right. When you make the conclusion, yeah, so this like kind of a missing the space for the details, but we cannot say this way, right? So we need to be more careful when you make the conclusion. It doesn't mean that the bedroom, if you reject the null hypothesis, it is fine, right? But if you fail to reject the null hypothesis, right? Does that mean that the bedroom doesn't have the significant linear relationship with the price? It doesn't mean like that, right? So let's look at the important note in our chapter notes. Right, the first thing you need to be careful is when you reject the null hypothesis, it is fine, because if you reject the null hypothesis, it means there is significant, strong relationship between the explanatory variable and the response variable. But if you fail to reject the null hypothesis, that means the beta j equals to 0 based on the t-test. It doesn't mean that the xj has no linear relationship to y. It means what? It means xj, the variable you are testing, contributes nothing to modeling y after allowing all for other predictors in the model. So what does that mean? So for example, if based on my regression, based on my parameter estimate table, for example, if your bedroom, this p-value is not 0.0073, if this p-value changed to 0.2, that means your 0.2 p-value is very large p-value, right? That means you fail to reject the null hypothesis. Then it doesn't mean that the bedroom has no significant linear relationship with the price, the house price. It just means that with the living area, this variable in the model, the bedroom, if you add the bedroom variable into the regression, it doesn't have significant contribution for this model. There's no significant additional contribution to this model based on the living area variable already in the model. Right, so here you need to be careful. If you fail to reject the null hypothesis, it doesn't mean that xj has no linear relationship to y. It means this variable contributes nothing to modeling y after allowing for other predictors in the model. Right, so this is the first thing you need to be careful. And then next thing is, we say in the multiple regression, it looks like each beta j tells us the effects of its associated predictor. But, right, so there are two things you need to be careful. The first one say the coefficient beta j can be different from 0 even when there's no simple linear relationship between y and xj. So what does that mean? We say we have the model which is mu of y equals to beta 0, beta 1 x1, beta 2 x2 until beta k xk. Right? Even though, for example, this x1 variable has no linear relationship with the response variable y, the corresponding coefficient beta 1 may not be exactly 0, can be some value with it. Right, so even though there's no linear relationship, it doesn't mean that beta 1 must be 0. Right, okay, so this is the first thing you need to be careful. Right, next one, it says it is even possible that the parameter estimates the slope change sign when a new variable enters the regression. We have a good example, right? So when we talked about the house price at the beginning, remember the example here, right? When we talk about the house price at the beginning, we did the simple regression, right? So for the simple regression, we only have one bedroom in our regression, and then the coefficient of the bedroom is positive. So we say when number of bedroom increase, the price of the house will also increase, right? But now when we add the living area into my regression, the coefficients all changed, and the coefficient for the bedroom changed to negative. Still remember why it changed to negative? And because when you interpret this coefficient, it means you need to fix the living area first. That means when you fix the living area, then if you have more bedrooms, the price will be decreased. So this is the good example that if you add more variables into your regression, the coefficient even can change the sign. It can be the same, but it will also be possible to change its sign. Alright, so this is the second note you need to be careful to understand what's going on. Alright, so it is even possible that the parameter estimate, which is the BJ's, right? The parameter estimate of the slope change sign when a new variable enters the regression. When the living area enters the regression, then it can be changed to negative because we need to fix the living area first. And then if you have more bedrooms, the house price will be decreased. Alright, so this is about the hypothesis test for each explanatory variable. Right, and then after we get the hypothesis test, of course we will get the confidence interval for each slope or each coefficient beta j. Right, so it will be the same. We have the beta j plus minus t star times the standard error of bj. Right, so bj you can find from the output, right? The standard error of bj you can also find the output. The only difference is the t star. Right, so here the t star will have the degree of freedom will be different with the last one. The last one will be n minus 2. But now if you have multiple regression, the degree of freedom is n minus k minus 1. So you will have already many degree of freedom right now, right? Okay, So the degree of freedom here is actually the same with the degree of freedom of SSE. Remember that? Right. So since it is the standard error, so it is the same with the standard with the degree of freedom of SSE. So to find the T star, you need to go to the T table, right, and then combine with alpha over 2 and the degree of freedom, right? So alpha over 2 degree of freedom to find your T star, and then you can find these two in the output, right? So the similar thing, right? So for example, let's say if you got, let's say, careful, right? So for example, if you get 95% confidence interval for example, beta 2, right, is given by, let's say, 11.2 to 11.8, right? So here is just I make a simple example, right? Okay. For example, if by the formula for beta 2 will be B2 plus minus T star times standard error of B2, right? If by this formula I got this confidence interval, how do you interpret this confidence interval? What does that mean? It will be similar, right? We say 95% confident that we say beta 2 falls in this interval, but it doesn't mean anything for your customer and or managers, right? Because they don't know what is beta 2, right? So actually you need to combine the interpretation of the confidence interval and the interpretation of beta 2, right? So remember how you interpret the beta 2 in the multiple regression. It means when the other variables value fixed, when other variables value fixed, then when this is for beta 2, right? So when x2 increased by 1 unit, the predicted y value will increase by this range, right? So for example, we say if this confidence interval is for the living area, right? So then we say 95%, we are 95% confident that when do not use two whens, right? Let's say if the number of bedrooms is fixed, then every 1 square foot increase in the living area, the house price is predicted to increase by this range. Got an idea? Right, so since we only have two variables in our regression, so here I just need to control the other variable, right, which is the number of bedrooms. But if you include totally 4 variables, then here you need to be control the other 3 variables value. All right, okay, and we are done with the hypothesis test for the regression. I just want to include one more topic, which is the R-square and adjusted R-square. All right, so let's talk about R-square and adjusted R-square. All right, so in the previous video, we have already talked about R-square a lot, right? Okay, so what is R-square again? R-square is the proportion. We have already repeated that again, right? Okay, so it will be proportion of the observed variation in Y that can be accounted by the regression or by X, right? So just like what I said here, right? When we talk about ANOVA table, we say SST is the total variation in Y. SSR is the variation can be accounted by the regression. SSE is the variation in Y caused by the random error, right? So actually the R-square is just a SSR divided by SSE, right? So the proportion of the SST, right? So it will be SSR divided by SST. So here I just have finally have a formal formula for the R-square. So here R-square, by the definition of R-square, it is equals to SSR divided by SST. And since SSR equals to SST minus SSE, it will equals to 1 minus SSE divided by SST, right? So it's the same thing. So this is the right definition for the real R-square. So here R-square is not just a square of the correlation. It has its own meaning. It shows the proportion of the observation in Y that can be accounted by the regression. All right, but when we look at the output after the R-square, there is always another one called R-square adjusted. Right, so what is the adjusted R-square? We say when we add more variable into the regression. So for example, we say for now we have the bedrooms and the living area in our regression. So that means we have 2 variables in our regression, and we have the R-square, which is 0.578. All right, okay, now if I do another regression, let's say the model dialog. All right, so if I add, we'll still use the price as the Y, and then we have these 2 variables inside our regression. But if I add the age into my regression, so that we have 3 explanatory variables in my regression. If I run that, I will have another regression, right? And then you can see that if I add one more variable into my regression, the R-square will be increasing, right? So increase from 57 to 0.59. And then I can do the same thing. Right, I can do the same thing. I can keep adding it, right? So I can keep adding fair places into it, right? So that I have 4, 1, 2, 3, 4, 5. Let's say add the bathroom also into it. Alright, so now I have 5 variables in my regression and then run it. And then you will see that the R-square will change to 0.60. It is larger than the first R-square. It is larger than this R-square. And then now it is 0.60. Alright, that means when we add the variables into, if we add the new variables into our model, it will always increase our R-square. Our R-square will always increase when new variables are added into our model. It doesn't matter whether this, let's try this, right? Alright, so let's do the experiment. So let's say I create another column and then I just randomly enter these numbers, right? So let's say I want a formula and the values from, let's say from 20 to 40. Alright, and then so apply it and then click OK. Alright, so actually this column I just assign random numbers between 20 to 40. Alright, and then you see these numbers should not have any relationship with the price, right? With the house price. So now if I do fit the model and then still use the price with it, but I'm adding all the variables into our regression, even though with this random column, right? And then we say run, right? So we see that right. So this output is the regression with all these variables. Alright, all these 5 variables. And this output is I add a really nothing related with the house price column, right, variable. And then I have 6 variables in my regression now. I'm adding 1 variable into our regression. You will see that there the R-square will also increase even though this variable has no relationship, has no contribution to this regression, this R-square will always increase. Alright, so this is the point I want to talk about. We say R-square will always increase when the new variables are added. It doesn't matter this new variable is related with the response variable or not related with the response variable. The R-square will always increase. That means for multiple regression, the R-square is not accurate anymore, right? Because we do not want to add the useless variable into our regression, right? So then we will have this adjusted R-square. So what is adjusted R-square? We say the adjusted R-square imposes a penalty on the correlation strength of the larger models. That means we want the model as short as possible. We want the the variables, the number of explanatory variables as small as possible so that we can save our money. We don't want to collect all these informations, right? So for example, if I want to make the prediction about the house price, I don't want to take time and spend money about the price, the bare price in the store, in the Kroger, right? So there's no relationship between these two, right? So actually, I don't want to spend money to collect all of these information because it is not useful. It is just a waste of time, waste of money, right? So we generate a penalty on for the larger models. All right, so that means the adjusted R-square will be in this formula. So you don't need to understand this formula. You just need to know that the adjusted R-square is a penalty to large models. Then the adjusted R-square will be much more useful than R-square in multiple regression. All right, so let's see this two again. Right, so we see that this output is based on 5 explanatory variables. This output is based on 6 of them with the useless one. Right, so for this case, you will find that the R-square still keep increasing. But if you look at adjusted R-square, the adjusted R-square kind of decreasing, right? Okay, because we are using a useless variable in this regression, right? So we need to compare the adjusted R-square in the multiple regression. So for this case, which model is better? Comparing by these two, of course, this is better because they have higher R-square adjusted. We have higher adjusted R-square. All right, so here we need to use, we say the adjusted R-square is used to compare the models. Actually, it's to compare the multiple regression models. Right, and R-square is to interpret your model. If you don't have another model to compare with, then you can use R-square to say, okay, if you don't have any other models, you only have this one, then you can use R-square to describe, okay, the R-square is 60.6048 is kind of not closer to 1, not closer to 0, right? It is in the middle of 0, 1. So it's kind of okay. The regression is kind of okay, right? But if you have another model to compare with, then you need to use the adjusted R-square to compare these two. You cannot compare the R-square if they have different number of explanatory variables, because one variable, we say model 1, model 2, right? So if we have model 1 includes, let's say, 3 variables, model 2 we have 4 variables, then if you compare R-square, the model 2 is always larger than model 1. But you need to use adjusted R-square. Right, so for adjusted R-square, we'll generate a penalty to useless explanatory variable. If this explanatory variable have some contributions on this regression, then the adjusted R-square will increase. The other way, if this explanatory variable is useless, and you will find the model 2 will be having smaller adjusted R-square than model 1. All right. Okay. So you remember the adjusted R-square is used to compare the multiple regressions, and R-square is to used to interpret your model. How good is your model? All right. And another thing we want to add here, we say R-square will always increase when we add variables into your regression. All right, so it doesn't matter whether this variable is useful or not, whether this variable contributes to the regression or not, the R-square will always increase. That's why we do not use R-square to compare the multiple regression. Instead, we use adjusted R-square. All right. So that's it for this video, and next video we'll talk about some other special cases. All right, so just let me know if you have any question about this part. I think it is not easy for you to understand this part about the adjusted R-square. Yes, and another thing is to compare the multiple regression, you also have another thing to compare. You can compare the adjusted R-square. You can also compare with their MSE. All right, okay, so to compare the models, we use the R-square and MSE, but for multiple regression, we need to replace the R-square with adjusted R-square. So we have these two things to compare the models. Right? If you have larger adjusted R-square, most of the time you should have small MSE. All right, okay, so that's all for today, and we'll talk about some other things in the next video. All right, so see you.